Good evening to all. Is the audio and video clear for everyone? Say. Thank you. So let us begin our today's session. In the previous class, we discussed about the finite fields as well as extensions and how we are defining the basis there, right? So do you have any queries on that concept to anyone? Tell me. If you have any doubts, you can ask now. So if not, I want to start a problem right now on today's session. Right. So this is the problem. Find a basis of q of root 3 comma root 5 over q. This was the question. Please take a note of that. After noting, please inform. So for our understanding, let us write the extension part here. The smallest field here is nothing but q. By adding one more element to it, we have another extension q of root 3. Then its next extension is q of root 3 comma root 5. This is the hierarchy if you talk. Now what happens? In the previous class, we discussed the theorem that whenever you have a hierarchy like A is subset of B, B is subset of C, like B is extension of A, C is extension of B, then by default C becomes the extension of A, and we calculate that C over A is equal to C over B into B over A. Did you recollect the concept of the theorem, what we mentioned? There you have used F subset of K subset of L in the previous class, I think. Accepted? The problem what we did. Yes or no? Now what happens? Here you are going to calculate the basis of this set over Q. So it is nothing but you are going to calculate the product formula what we did actually. So you have to compute a basis over this. So here you will get a dimension. Again, you will have to compute a basis over this. Here you will get a dimension. So combining these two bases, you will get the main basis for this set over Q. Is the ideology clear? Now comparing this between two sets, what are the element different for us? Q of root 3 and Q of root 3 comma root 5. Tell me. Root 5 is the separate element when compared to this set. Accepted? Right. So we have to say that root 5 is algebraic over this set. In other words, root 5 satisfies an irreducible polynomial over this set. That was the context. So if you take alpha is equal to root 5, then squaring on both sides, alpha square is equal to 5. So alpha square minus 5 equal to 0. Therefore, x square minus 5 equal to 0 is the polynomial satisfied by alpha. Accepted? Is my voice clear to all? Yes or no? Clear for all? Thank you. Now, what is the degree of this polynomial? 4. If you calculate the dimension q of root 3 comma root 5 over q of root 3, this is nothing but 2. How this 2 came? It is nothing but the degree of irreducible polynomial over q of root 3. And this is that polynomial. And obviously we say that this polynomial is irreducible. How do we specify that this polynomial is irreducible? By simply applying the Einstein criterion. We have the Einstein criterion, right? If you take the prime number p is equal to 5, p divides the constant term, p divides x coefficient, p does not divide x square coefficient, and p square does not divide constant term 5 here. So the prime number is equal to 5, which satisfies Einstein criteria for the polynomial x square minus 5 equal to 0. However, in exam, we don't mention that this is the irreducible polynomial. By default, we consider that x square minus 5 is an irreducible polynomial over the set q of root 3. Okay? Because its root is nothing but root 5. Root 5 is not at all an element in this q of root 3. Because the fundamental thing is irreducible means it will not contain any root. Reducible means it will possess a root. Since root 5 is not an element, by default it is irreducible. There is no need to prove that separately. Clear? Now, let us calculate the other part. Have you noted this? Say. Now, we are going to other thing. So, we are calculating q of root 3 over q. So, here, if you want to know the dimension of q of root 3 over q, it is also nothing but 2. Because if you take alpha is equal to root 3, squaring on both sides, alpha square equal to 3. So alpha square minus 3 equal to 0. Accepted? Therefore, root 3 is a root of the polynomial x square minus 3 equal to 0, and this is the irreducible polynomial. Therefore, what happens now? For this, the dimension is 2, and this is nothing but the degree of the irreducible polynomial. That's why its dimension is 2. Now, coming for the main solution, if you apply the hierarchy, q of root 3 root 5 over q is equivalent to q of root 3 root 5 over q of root 3 into q of root 3 over q. So this is nothing but the dimension is 2 here, the dimension is 2 here, equal to 4. That was the final solution. Please understand that here we have calculated the dimension. It means that how many elements will be there in the basis. But we didn't calculate the dimension, we didn't calculate the basis so far. Okay? You first take a note of that. Then I will specify you how to calculate the basis value. After noting, please inform. Now, while calculating the basis, the technique here is, in the previous class, we did a problem that whenever you have a basis alpha 1, alpha 2, so on, alpha n for one vector space, if we have another basis beta 1, beta 2, so on, beta m for the other vector space, while considering the product set is taken as alpha I beta j, and this will become the basis for the product set while proving the extension of vector spaces. Did you reconsider that of the previous class taken from that? If you have noted the proof as well, say yes or no. And one more thing is, whenever you say that alpha is a root of the polynomial of degree n, then what happens? The basis will contain the values of the form alpha 1, alpha, alpha square, so on, alpha power n minus 1. This is the basis actually. It means that you know that dimension is n, alpha is satisfying a polynomial of degree n, then by default the total values in the basis are nothing but n, and the basis will be formed by these elements 1, alpha, alpha square, so on, alpha power n minus 1. So here, while considering the dimension, you have taken that root 5 is the element, and you know that root 5 satisfies the polynomial x square minus 5 equal to 0. So what is the degree of the polynomial? 2. So if you consider this vector space, the basis is nothing but 1 comma root 5. So for the first vector space, the basis is nothing but 1 comma root 5. So here we have taken that root 3 is algebraic over Q. There you have taken the polynomial x square minus 3 is equal to 0. Here also the degree of the polynomial is 2. Hence its basis is 1 comma root 3 as 1 alpha, alpha square, so on, alpha power n minus 1. This technique if you apply here. So you know that this is the basis for one vector space. This is the other basis for another vector space. Now, whenever you know two bases, how to formulate the resultant basis while considering the product? This is the formula. So multiplying one basis elements with the other basis elements. So the final basis, what you are writing is, if you pick up the first element, with this first element multiply these values. So 1 root 5. If you pick up the second element, multiply with these values. So root 3 comma root 15. So this is the basis having 4 elements for the resultant set. That is our final solution. Okay. Please take a note of that. If anybody has any other queries, you can ask. Any queries for anybody? After noting, please inform. Can I erase that? Right. So there is one small result. Let us discuss on that. Now, if K is an extension of F, then K is equal to F if and only if K over F equal to 1. K is equal to F if and only if K over F equal to 1. Please take a note of that result. Shall I proceed? Right. Now, it contains main part as well as converse part. Let us take the main part. Suppose K is equal to F. Now you consider the dimension of K over F. It is nothing but K over K. Or you can write it as F over F, whatever the case may be. So this is nothing but 1, because it is just like calculating order of the element by order of the element, the number of elements in the set. So gets cancelled, value is 1. So main part is a trivial case. There is no need to prove that exclusively. So coming for the converse part, so you take that K over F is equal to 1. So by default, we need to understand K is an extension of F. So our picture is nothing but K is the large set, F is a part of it, F is subset of K. So we have to prove that K is equal to F. This is our claim. So it is nothing but, it is enough if you have shown that K subset of F. It means if you take any element in K that should belong to F, then K is subset of F, then both will be equal. That is the idea. Accepted? Say. Now, let us take an element first. So here you can say that since K over F is equal to 1, obviously you will get a vector space K over F and it has a basis. The basis contains an element A. Let us take that the basis contains an element A because the basis having one element. So let that or let A belongs to K be the element. Let A belongs to K be the element. Now, as we have known that this is the basis, what does it mean? Whatever the element you take in the vector space, that can be written as a linear combination of bases. So, the field K itself contains the multiplicative identity 1. So, I can write the value 1 is equal to some value into A, just like the linear combination. So, let us give a name for it. The name is alpha, where alpha belongs to F. As 1 belongs to K, I have taken that A belongs to be the basis element. So, this is the way you can write 1 is equal to alpha into A. So, multiplying both sides with alpha inverse, you can say that A is equal to alpha inverse. Since F is field, so alpha inverse also belongs to F. So A is equal to alpha inverse. So our intention is to prove that K subset of F. Now let us take any element in K. Say I have taken the value B belongs to K. As this is the basis element, whatever the value you consider, it must be written as a linear combination of that. So you can write B is equal to beta into A, because singleton A is the basis. As we know, A is equal to alpha inverse. This is nothing but beta into alpha inverse. Here beta belongs to F. Now see what happened. I have mentioned that alpha inverse belongs to F. I have mentioned that beta belongs to F. Since F is a field, the product also belongs to F. Therefore, B is equal to beta into alpha inverse belongs to F. Therefore, K is subset of F. Therefore, F is equal to K will hold. Please check on that. Please take a note of that. Any questions you can ask. Are you getting the idea behind it? Say, any questions, any doubts? Right, I will take the other one. May I? Okay. So based on this result, there is one small result that suppose L is an extension of F such that L over F is equal to P. P is a prime number. Then there exist no subfields between L and F. This was the problem. Please take a note of that. After noting, please inform. Right? Now, here, if you understand the previous part, it says that whenever you have a part that A over B is equal to 1, immediately A is equal to B. This is the thing we have learned in the previous result. So whenever you consider two fields, if the basis contains only one element, then these two fields are becoming equal. That is the idea. Okay? You please take a note of that. Now, from this, as per the question task is concerned, this is the actual thing given. F is subfield, L is the extension. He is saying that whenever you have a vector space L over F such that dimension is P, it means that if you calculate a basis for L, it contains exactly P elements where P is a prime number. So the basis will contain 2 elements, 3 elements, 5 elements, 11 elements, etc., etc. So the number of elements in the basis is a prime number. Then you cannot get a subfield between these two. That was the actual thing. You cannot get a subfield between these two. Are you clear with this? Now, how we are going to prove this? If we have taken any subfield between the two, let us say I have taken a subfield K. Now what I am saying that either these two will become equal or these two will become equal. My intention is I am going to say that either L is equal to K or K is equal to F. Then what happens? We are indirectly saying that there is no subfield which is lying between these two. Accepted? There is no subfield which is lying between these two. That is indirectly what I am saying. Yes or no? If I have proved that either these two are equal or these two are equal, it means that there is no field which is intermediate between these two sets, isn't it? It is just like the case of maximal ideal, what we did earlier. There is no ideal between the ring and the ideal given, so it becomes the maximal. Say, the similar logic we are applying here. Now, for the solution part, if you consider, so let us take that K is a subfield of L such that F subset of K subset of L. Let us take that. Now, the yesterday theorem I am using here. So, immediately we can say that L over F is equal to L over K into K over F. Since the value is finite on the left hand side, right side value is also finite. And in the problem it is given that this is P. Now, since P is a prime number, since it won't have the proper divisors, either this number should be 1 or this number should be 1. Therefore, L over K must be equal to 1 or K over F must be equal to 1. It has the only possibility like this. So, whatever the possibility you take, from this you can say that L is equal to K or K is equal to F. It means that there is no subfield between F and L. In this way we prove the result. Please observe that. So after taking the note, please inform. Right. Any other questions for anybody on this? Right. Now I ask you a simple question. So what is meant by a finite extension? So far the class discussions are concerned, what is meant by a finite extension? Any one of you? What is meant by a finite extension? If I mentioned that L is finite extension of F, it is by default means that L over F is finite. So what does it mean? It gives what to us? It gives what to us? Yes, basis is finite. In particular, you are saying that this value is less than infinity, it is a finite value. It means that if you take L over F is equal to N, a finite value, so you are having a basis for L over F with N elements. Accepted? So based on this, one small result is every finite extension is an algebraic extension. Every finite extension is an algebraic extension. That was the thing given. So Can you specify what is meant by algebraic extension? I have given the definition already. What is meant by algebraic extension? Are you getting it or not? Yeah. Then, what is meant by an element algebraic over a field? An element algebraic over a field? Anybody? Let me say, I have taken a field F. If I say that an element A is algebraic over F, it means that A satisfies a non-constant polynomial and the polynomial is belonging to F. So the coefficient of the polynomial will belong to the field F and A is the root of that polynomial. In other words, A satisfies a polynomial whose coefficients are taken over F. That was the actual idea, that an element is algebraic over a field. Okay? Clear? So whenever you take that field and subfield, so this is F, the subfield, and this is L, the extension. If I say that this extension is algebraic extension, it means that whatever the element L you consider, then each element is algebraic over F. If I say that L contains 100 elements, each of the 100 elements is algebraic over F. That means each element is satisfying a polynomial whose coefficients are taken over F. Okay? This is the definition of algebraic extension. Now what I am saying, if you take a finite extension, it is algebraic. It means that I have considered an extension like this. Let me say the extension value is n. It means I can find a basis. It contains n elements. Now what I am saying, that each and every element of that is algebraic over this. So every finite extension will become algebraic. That is actually I am saying. Okay? And the converse of the result is not true. So if you take an algebraic extension, that need not be finite. For that we have similar examples, right? That we discuss in the next time. So at present our main interest is, if you take a finite extension, that is always algebraic. So for the proof of it, let us take the same example. F is the subfield of L. So L is the extension of F, and let us take that L over F is finite and L over F is equal to n. Now to prove that the algebraic nature, let us take that A is an element belonging to L. A is an element belonging to L. Now, if you understand the definition of basis, whenever you specify that this is the basis, then if you take any element more than the number of elements of the basis, then it will become linearly dependent. Let me say, if the basis contains 3 elements. Now, if you take any set having more than 3 elements, then it will become linearly dependent. Have you known this result or not from the vector spaces concept? If you don't know, then please take a note of this. If you know the number of elements in the basis, if you consider a set in the vector space having more than the number of elements in the basis, then it is always linearly dependent. Now, I have taken element A. Now, I am considering the set 1, A square, so on, A power n values. Please understand, L is a field basically. If you take A belongs to L, A square also belongs to L, A cube belongs to L, A power n also belongs to L. Accepted? Because it is a field, I am simply multiplying the values. So, how many elements are there here? N plus 1 elements. Here I got n plus 1 elements. A power 1 to A power n values, 1 is additional, so I got n plus 1 elements. Since the dimension is n, it means it has the largest independent set is n, having n elements. So this set is nothing but linearly dependent set, because the basis is n only. So if you take any set having more than n elements, it is linearly dependent set. It is not linearly independent. So what is meant by linearly dependent definition? If you say that, let us write a simple example. If I said that alpha, beta, gamma is a linearly dependent set, from the very definition, it means that I can find scalars, say A, B, C. Scalars means numbers. I can find numbers A, B, C such that A alpha plus B beta plus C gamma is equal to 0. On summing all the values, I will get 0 as the result. And the numbers A, B, C are non-zero. It means that at least one of A, B, C, a value is non-zero. This is the definition. Clear? Are you clear? Right. So, applying the same definition here, since this set is having n plus 1 elements, I can say that I can find a linear combination. The result is 0, in which the numbers what I have written are non-zero. It means all the numbers may be non-zero, at least some of them are non-zero. That was the idea, the definition of linearly dependent set. So immediately I can say that I can find the set of scalars, right? So I am taking the scalars as 1 into B naught plus A into B1 plus A square into B2 plus so on plus A power n into Bn is equal to 0. Right? So here the coefficients B0, B1, B2, so on, Bn are taken in the field F, because this is the linearly dependent set over the field F. The coefficients are taken in F. Clear? Anybody has any confusion so far what I did? Right. Now please understand, if you clearly observe that, from this we can say that you have obtained a polynomial B0 plus B1x plus so on plus Bn x power n is equal to 0. For this polynomial, A is the root. See, if I substitute A there, I am getting 0 actually here. You correlate the two values. Observe it. Therefore, a is a value. It is satisfying a polynomial, and the coefficients of the polynomial are belonging to the field f, isn't it? Therefore, by definition, a is algebraic over f. The proof is simply 3 lines. Initially, I have taken an element A belongs to L. Now, I know that if we have taken that the dimension is n, any set having more than n elements is dependent. So I have taken the set like this. This is the dependent set. Now I have written the dependent set definition. From this, immediately I conclude that this is the polynomial satisfied by A. So these 3 steps I have explained so far. Now, immediately I can say that A is satisfying a polynomial, hence A is algebraic over F. I have taken A randomly any value in L. So whatever the value you take in L, it is becoming algebraic over F. Therefore, L is algebraic extension of F. Therefore, every finite extension is algebraic extension. Okay? Any other queries so far for anybody? Please take a note of that. Then I will discuss a new one. After noting, please inform. Shall I proceed? Please tell. Okay. Actually, there is one more result that suppose you take a field F. Now, over this field, you consider an irreducible polynomial. Then we can say that you can find an extension for F in which this polynomial is reducible. So an irreducible polynomial will become reducible in the extension. In the other way, we can say that whenever you have taken an irreducible polynomial over F, you can find an extension of F in which this polynomial possesses a root. Okay? You please take a note of that, and I am going to prove this, the result. Okay? Shall I proceed? Yeah. Now I am giving the definition as well as the result. Let f of x belongs to f of x of degree n greater than or equal to 1. Right? Then there exists an extension of f. Say the extension is nothing but the value k, such that k over f is less than or equal to n factorial. And k has n roots of f of x. Please take a note of that, then I will discuss. After noting, please inform. Right. So if you observe that I have taken a polynomial of degree n may be 1 or more than 1. So if you take an nth degree polynomial, then how many roots it will possess? N roots, isn't it? So I am saying that you can find an extension of f, say the extension name is k. So in this set, it contains all the roots of this polynomial f of x. If you say there are 3 roots for f of x, all the 3 roots will be in this extension. If you take n roots, all the n roots will be in this extension. And what will be the basis? The basis contains less than or equal to n factorial elements. This is the concept of the theorem or the result. Okay? Any questions for that? Now, the interesting thing is we are going to prove the result by means of induction. So we are applying the technique of mathematical induction on the degree of the polynomial. So how do we prove? For n is equal to 1, we have to prove the result. For the result holds up to the values n minus 1, and we have to prove it for n, isn't it? The concept of mathematical induction. Agreed? So let us take the case that n is equal to 1. Now what happens? F of x is a polynomial of degree n. It is nothing but a linear polynomial. So obviously f of x will be of the form ax plus b, where the coefficients a comma b are belonging to the field f. Now what happens? If you make that equal to 0, so you can say ax plus b equal to 0 implies x is equal to minus b by a. Accepted? Now what happens? This value minus b by a, in other words minus b into a inverse, is root of f. If you substitute minus b a inverse, you are getting 0. Yes or no? And here, what is the place of this value? In other words, in what set this element belongs? If you understand that the coefficients are as well as taken as f, so a is an element in f, b is an element in f, so a inverse also belongs to f because f is the field. So minus b a inverse also belongs to the f. By closure law, this element belongs to f. So f of x is having a root minus b a inverse. And how to define the extension? As we did a result earlier, we know that k over f is equal to 1 if and only if k is equal to f. So just like that, I will take the extension as f itself. I will take the extension as f itself. Okay? So therefore, by n is equal to 1, the result is true. So apart from taking k as a separate set, the extension, I have taken that k is nothing but f itself because it is possessing the root, right? So here the extension is not a different set, it is f itself because f is subset of f. Are you clear or not? Let me say, this is the set F. I need to calculate a extension K for F. Accepted? Now, please don't misunderstand that K is totally a separate of this. I am saying that in the first case, if you take n is equal to 1, K and F both are equal. Because F itself is having the root, right? Whatever the first degree polynomial you take, that root is nothing but belonging to the field F itself. Therefore, here K and F not of different sets, they are the same set. So I am taking F for F is equal to 1. The extension is nothing but F itself. So this property automatically satisfied. Agree? Now, for n is equal to 1, the result is true. Now let us take the induction hypothesis. What it means, if you take a polynomial of degree greater than 1, then it will possess all the roots in an extension. In other words, all the roots of this polynomial will be in an extension, and I am taking the degree of the polynomial up to n, not equal to n. Let me say, if I take n is equal to 50, so induction hypothesis says that whatever the polynomial you consider up to degree 49, degree 1, degree 2, degree 3, up to degree 49, whatever the polynomial you consider, obviously you will get an extension of f in which all the roots of that polynomial will belong. Clear? The induction hypothesis. Say. Now we have to prove for n. Now let us take that f of x is a polynomial of degree n. Let us take the case now. So there is a known result that always whenever you take a polynomial, obviously you will get an extension in which at least one root will come. Before going to start this result, I have mentioned, whenever you take a polynomial, always you will get an extension in which the root comes. So let us say alpha is root of f of x. Now what happens? X minus alpha is factor of f of x. So you can write f of x is equal to x minus alpha into some other polynomial, say q of x. Accepted? Right. Now, if you compare the degree on both sides, the degree of f of x is n. Since its degree is 1, obviously its degree must be n minus 1. Accepted? So, q of x is a polynomial whose degree is up to the value less than n. It is n minus 1. Here, for q of x, we can apply the induction hypothesis. Therefore, you can find an extension of f such that all the roots of q of x will belong to that. All the roots of q of x will belong to that. Now, you can write the extension as, I am going to take the hierarchy like this, f, l, k. So here you are taking the value as, let me say, I am taking the polynomial q of x. Here I am taking the polynomial x minus alpha. So if you write the hierarchy, it will come like this. So K over F is equal to K over L into L over F. So for L over F, I will take n minus 1 factorial because I have taken the polynomial Q of X. For K over L, we know that the degree of the polynomial may be less than or equal to n. Right? We don't know what polynomial it is satisfying. The least we can take the first degree polynomial. So by combining these two, I will get n into n minus 1 factorial, nothing but n factorial. This proves the result. Okay, so please take a note of that. Now I just want to give another definition or another result, let me say. Just give me a moment, I will fetch it for you. So this is the result. Suppose E is an extension of F. Now you take two elements in E, say A comma B, and take that A comma B are algebraic over F. Immediately you can have the respective vector spaces as well as degrees. So let us take that F of A over F is equal to M, F of B over F is equal to N, also GCD of M comma N equal to 1. You take this one. Now it is saying that if we calculate F of AB over F, this is equal to Mn. This is the claim you have to prove. Please take a note of that. Right. Now how to prove this? Can you give any example for it? The strategy of proving this? Anybody? Yes or no? Right? Then I will give the idea. So let us take the part like this. The smallest one is F. Say this is F of A. This is F of A comma B. This is one kind of extension line. You can fill in the other way that F, F of B, F of AB. Accepted? The extension line, all of you. So from this, if you consider this one, f of AB over f is equal to agree, applying the extension properties while writing the hierarchy. So actually we don't know what is this value. F of AB over f, we don't know what is this value. Let us say this value is k, say. So this is equal to, you got the result, f of AB over f of B into, this is n. So from this we can say that n divides k. Accepted? In other words, you can say n is less than or equal to k. Right. Similarly, if you take this extension, applying the hierarchy, you have f of AB over f is equal to f of AB over f of A into f of A over f. So from this, you can say that k is equal to f of AB over f of A into m. Therefore, we can say that m divides k. Therefore, m is less than or equal to k. As we know, m is dividing k and n is dividing k. Therefore, we can say that mn divides k. The product also divides k. So first you take a note of this hierarchy and the result. Mn divides k, that we got actually. Please take a note of that. Right. Now, we don't know actually what is this value. So let us give a number for this one. So from this, what we can say? If you take f of AB over f of B, let us say that value is some p. From that, what we can say? So B is algebraic over, A is algebraic over f of B. So it satisfies a polynomial of degree p, isn't it? So on the whole, I just want to say that you are proving that k is less than or equal to mn as well as mn is less than or equal to k. Therefore, both will become equal. That is the underlined idea. Now, how to write the small writing there? If you take some value there, how do you write? We just take a note of that. This kind of result we will get actually. So, however, I will give the clear data again. So the underlying logic is this. You just take a note of that. So I will give the full clarity separately, right? You just take a note of that for this part. So I will give the clarity for separately, right? I have a small confusion over this result. I will give that separately, right? I will give the posting separately for you, right? So at present, I just want to close our session. Tomorrow we will meet with the new concept that is splitting fields. For this, I will give a separate ideology. So we discuss this topic tomorrow, right? Thank you very much. So I just want to wind up here now. I have a small confusion over this result. I just want to try it in a different manner. Thank you. So tomorrow's topic will be on splitting fields. So after having this splitting fields, we have one more thing called, say, problems based on Silo theorems. And there is one small concept called algebraically closed fields. From this, we have a small question given in 2017 UPSC based on algebraically closed fields. So first we discuss with the splitting fields, then with this part. So after this, we have done with the complete part of finite fields. Then we have take one or two problems based on Silo theorems. This is the complete thing of abstract algebra. So then I think Venkana sir will come up because I just want to take a break. So Venkana sir will come up. So if I am taking the next session also, then I will start with numerical methods. Otherwise, Venkana sir will come and he will take his part. In the middle, I will join. That was the upcoming plan for the next chapter. Okay. So you can ask Venkana sir, maybe he is starting with statics and dynamics. I hope so. Because majority of the people have not covered it with that thing. Statics and dynamics. Have you studied that earlier in the batch? So far what you joined? Then that will be the next topic, I hope so. most probably. Or you can ask Venkana sir what he is going to take. Sir will give you the list of reference books, and the list is available in the website, right? The list of books are available in the website given, isn't it? Yes, that you can follow. If you have any special books, if you want to refer, then you can ask sir directly. Right. So that was the upcoming plan for taking the classes. Thank you.